Hi, and welcome to online lecture 30. Today we will be discussing the chi-square test. This is the last test we will actually be discussing in this class. And then I have just a little bit of pulling together the tests at the end. Okay, so let's get started. This actually is a great test because it allows us to do a little bit of review. Okay, so let's start in by talking about the kinds of variables that we talked about at the beginning of the semester. First kind I want to talk about is the nominal or qualitative variable. Remember, this is the kind of variable that has few values, usually names or categories with no natural order. In other words, things like gender, race, eye color, favorite color, religious affiliation, political orientation, all those sort of things are nominal variables, right? There's no natural order to those. Okay. Now, the ordinal, interval, and ratio, or quantitative or continuous variables, are variables that are numeric. They have many values. They use numbers. There is a natural order. In other words, whether you were first, second, third in a race, or in other words, what the temperature is today. Is it 40 degrees or 80 degrees? Or what is the height of the average height of basketball players? Or what is the time it took to complete this cognitive task? Those are all different kinds of quantitative continuous variables. Okay, so where am I going with this? Let's look. Now, when we talked about certain tests, all the tests that we've used so far have involved at least one quantitative variable. When we talked about the z-tests, the different t-tests, the one-way ANOVA, the repeated measures ANOVA, and the factorial ANOVA, we had one quantitative continuous variable. When we talked about correlation and simple linear regression, we had two quantitative continuous variables. We've had one, we've had two. Where are we going with this? And now it's time for something completely different. What if you're not using a quantitative variable at all? Zero quantitative variables. Well, we're not going to have our usual parametric assumptions. What does that mean? Remember, all along we keep worrying about if our population is normally distributed. That goes away. We're not going to worry about our population being normally distributed. We're going to use what's called a non-parametric or distribution-free statistical test. A non-parametric or distribution-free statistical test. Okay. And to that end, we're going to talk about the chi-square. Well, the chi-square actually has many different situations, but we're just going to talk about two different situations for the chi-square test. First, when you have just one qualitative variable and you want to compare which group people are most likely to belong to. Well, that's called the chi-square test for goodness of fit. Are volunteers for psychology experiments more likely to be male or female? Now, I started off with just two groups here, but you can have more than two groups. We could add a third gender group, non-binary. We could add a fourth and fifth, whatever you want there. But we can only have one variable, one nominal variable. Okay. The next situation is when we have two qualitative variables, two nominal variables, and we want to know if they are independent of each other. We want to know if they are independent of each other. This is called the chi-square test for independence. Is gender independent of color preference? Okay. Again, we can have as many categories of gender as we like, as many colors as we like. That's not a problem. But we can only have two qualitative variables. Okay. So we're going to mainly focus on the first situation, the chi-square test for goodness of fit. We're mainly going to focus on that in terms of going through a full example and understanding that one. For the other one, I mainly want you to know what it is and where it applies. Okay. So let's look at this. Are people more likely to belong to one group than another? That's the main question of a chi-square test for goodness of fit. And if we want to talk in very general terms, we could say our alternative hypothesis are people are more likely to belong to certain groups or categories. And the null hypothesis is that people are not more likely to belong to certain groups or categories. Okay, still adding the word not to get from alternative to null. So let's go through an example together. And we're going to talk about distribution of eye color for a sample, where our n equals 40. Okay. Now, in this case, we have gotten some observed frequencies, and that's what they're called. That's what our data is called in this case, observed frequencies. We have 12 people who had blue eyes, 21 reported brown eyes, 3 reported green eyes, 4 reported other color eyes. So in a sample of data, individuals in each category are counted, and those counts are, as I said, the observed frequencies. Now, the only other big number we deal with here is the expected frequency. Now, that's the frequency value that's predicted from the null hypothesis and the sample size. So the expected frequency equals total n times the proportion expected for a particular cell. Now, if we look back to our null hypothesis, we would see that we really expected eye color to be equal across our groups. So if we expect eye color to be equal across our groups, then we would just take our total n, which is 40, times the proportion expected for each cell. Well, if we expect the 4 categories to be equal, that's 0.25 per category, or 25%. So we take 25%, or 0.25 times 40. Okay, and then we would get 10 for each category. All right, we'll come back to that. So let's now talk about our assumptions. First of all, we have to have independence of observations. A person can't appear in more than one cell or category. So what if you had a person who said, well, my eyes are kind of blue-green? What do you do with them? Well, you can't put them in both the blue and the green category. You could put them in the other category. That's something you could do. And all expected frequencies have to be at least 5. They have to be at least 5. And if not, you use an exact test. Okay. So here we are back with our distribution of eye color. We already talked about this blue, brown, green, and other, and how we think that our expected frequencies would probably be 10, 10, 10, 10. But let's say, just for fun, that we knew something about genetics. And we knew that eye color was not evenly distributed across the population. In fact, we knew that as on average, 50% of people have brown, 20% of people have blue eyes, 15% of people have green eyes, and 15% of people have another color of eye. Let's say that was our null hypothesis, that we wanted to see if it differed, if what we got with this sample differed from the typical pattern we see in the population. Okay, well then we just take each percentage and multiply it by our total. So what did I say for brown? I said 50%, right? So 0.50 times 40. Well, my expected value here would be 20. Next, let's do blue. What did I say there? I said 20%. So 40 times 0.20 equals 8. Now I expect 8 to have blue colored eyes. And I would go on and do the same calculations for 40 times 0.15 for green and 40 times 0.15 for other. And it's okay if I get a decimal answer. That's not a problem. Okay. In a sample of data, individuals in each category are counted. Oh, sorry, did I go backwards on you? I did. Sorry about that. So chi-squares aren't for continuous data. Challenge accepted. So this is just a little reminder that chi-squares are for nominal qualitative data. All right. So now let's go through one more example together, and this time we'll go through it all the way through. Okay. So this is kind of cool. Fielding came up with this experiment regarding abstract art. And Fielding asks, you know, since it's abstract art, technically any of these four sides could be the top side. So which way is up? And Fielding believes that one or more orientations of this painting will be preferred. So here we go with the alternative. There is a preference for one or more orientations of the painting, and no, there is not a preference for orientation of the painting. Okay, so here again, we have top up correct 18, bottom up 17, left side 7, right side 8. These are our observed frequencies. These are our data, what we collected. And when we asked people, this is what they said. Okay, 18 said top, 17, and so on and so forth. Okay. Now for the expected frequency, remember that's the frequency value that is predicted from the null hypothesis and the sample size. So our expected frequency equals the total n times the proportion expected for a particular cell. Total n times the proportion expected for a particular cell. Now, again, this is one where we predicted that they would all be even across the categories. So all we had to do was take our total, which was 50, and we get the 50 by adding 18 plus 17 plus 7 plus 8, right? And then we take that 50 times 0.25, right? Because we expect, or you could technically take 50 divided by 4 if you have an equal expected proportion for each cell. You could take 50 divided by 4, or 50 times, take 25% of 50, or 0.25 times 50. They'll all give you the same answer, which is 12.5. 12.5. Okay. So I like to take 0.25 times 50 because that's exactly how the formula is written. Okay. So how do we actually calculate the chi-square test? And this again is the chi-square test for goodness of fit we're talking about. Our notation is chi-square. Okay, so the funny X is the Greek letter chi, and the square is square. O or FO is the observed frequency. E or FE is the expected frequency. So we land with our chi-square statistic with these formulas are equivalent. With one of these two formulas, they're the same. I like the one on the left, so we're going to talk about that one, okay? So we have observed frequency for a cell minus expected frequency for a cell, square that, and divide by the expected frequency. Now we move on to the next cell. Observed minus expected, square it, divide by E, expected. Okay. And we move on to the next cell and the next cell and do the same thing. When we have all four cells figured out, we add up those numbers. And that's our chi-square. Now, I want to point out that in previous kinds of tests, what you typically did was you subtracted, squared, added, and then divided. This is a little bit different, right? Because now we're going to subtract, square, divide, add. I switch the last two steps. Subtract, square, divide, add. Okay. So now let's work through this example together. We have our observed frequencies, we have our expected frequencies. So we take 18 minus 12.5 squared divided by 12.5 equals 2.42. 17 minus 12.5 squared, right? So the first thing you're going to do is subtract, then square that number, then divide by 12.5. That's your answer. Next is 7 minus 12.5, square that, divide by 12.5 equals 2.42 again. And finally, 8 minus 12.5 squared divided by 12.5 equals 1.62. Okay. Now all that's left to do is add those numbers up. So we add up our 2.42, our 1.62, our 2.42, our 1.62, and we get 8.08. That's our chi-square value. That's our chi-square value. Okay. So what are we really doing with this chi-square test? Well, basically what we're doing is we're not rejecting the null if the discrepancy between the observed and expected is small. But we are rejecting the null if the discrepancy, if the difference between the observed and expected values is large, right? So we're looking for, because we like to reject the null, we're looking for a large discrepancy between observed and expected. And that makes sense because the expected is our null hypothesis. Well, we want to be different from the null hypothesis, right? Okay. Let's talk a little bit about the distribution and degrees of freedom. Okay, so all chi-square values are greater than or equal to 0, just like the f. Remember, f is always greater than or equal to 0, so is chi-square. Okay, and just like ANOVA for the chi-square test, we are only going to consider two-tailed tests here. We're not going to worry about one-tailed tests. Okay. The chi-square distribution is positively skewed, and different distributions depending on the DF. Well, we're used to that. We saw that before. Now, the degrees of freedom for the goodness of fit test is pretty straightforward. It's the number of categories minus 1. So in our previous example, we had 4 categories for the 4 orientations of the painting. 4 minus 1 gives us 3. So here's the chi-square distribution in the critical region. This is our cutoff region over here on the right. Notice how skewed it is, right? Okay. And here are the chi-square distributions for different values of degrees of freedom. So the more categories you have in this case, the less skewed it is. I'm not going to say it's normal, but it's a little bit less skewed. Okay. Now, the critical value for chi-square is located in the table of critical tabled values according to the degrees of freedom and alpha. You're going to, I know it's another table, but it's our last table, and I think you're going to like this one because it's really a short table. Okay, so here we are again with our example. Remember, we got a chi-square of 8.08 and a DF of 3. DF of 3. Here is our table. So our DF is 3. Our alpha was 0.05. The number we're trying to beat is 7.815. So again, that's 0.05, 3, 7.815 is the number to beat. And remember, we don't have to worry about positive and negative because chi-square is always positive. So did we beat it? Did we beat 7.815 with 8.08? Sure, we did. We did. So in this case, we can reject the null. Okay, so now let's look at how it looks in SPSS. Very similar, right? We get our observed ends in this category, our expected ends in this category, and it even is nice enough to calculate the difference between the two for us, right? It's just subtracting 18 minus 12.5, 17 minus 12.5, 7 minus 12.5, 8 minus 12.5. And then it goes on to give us our chi-square test for goodness of fit. 8.08. They give an extra O here. DF of 3. P-value is 0.044. Less than 0.05? Yep, less than 0.05. So this is significant, so we can reject the null. And remember, it's a two-tailed test, so we don't have to worry about anything else. It's significant, we get to reject the null. Now, we could have, to make sure we didn't violate the assumption of that not having less than 5 expected per cell, we could have looked here, but SPSS is really nice and tells us right here at the bottom, 0 cells have expected frequencies less than 5. Great, we're in good shape. The minimum expected cell frequency is 12.5. So we don't have any cells with an expected frequency less than 5. That is good news. That means we met the assumption and we have no problems. Okay. Okay, so now what we're going to do is move on to the comparison of all the tests. So that's the end of the chi-square test that we're going to talk about together, okay, in lecture format. However, now I want to do this nice comparison of tests for you, okay? So let's talk about all the tests we've talked about this semester, okay? First, we're going to look at the tests that all have one continuous variable. That's the z-test, the t-test for a single sample, the t-test for dependent samples, the t-test for independent samples, one-way ANOVA, repeated measures ANOVA, and factorial ANOVA. Okay, so the point of this exercise is to figure out how we know which one's different from the other. Okay, so I'm going to go through and tell you how we know what's different about all of these tests from the other one, because you'll notice they all at the bottom detect differences. That's the goal of all of them. Okay, so here's the big difference for the z-test. The population variance is known. Remember, that's some form of that sigma, the O with the little tail on it. That means we either know sigma or sigma squared or the or sigma x bar. We know some form of the population variance. Okay. Now, for the t-test for a single sample, we know the population mean, but that's not enough because we also know the population mean for the z-test. So we also have to look and see that we don't know the population variance. If you have that combination of knowing the population mean and not knowing the population variance, well, then you have a t-test for a single sample. Okay, let's move on to the t-test for dependent samples. What's different here? 2 values or scores per participant. Remember, this is a repeated measures test, and we have each person has been tested twice, or each person has been tested under 2 different conditions. Okay, all right. That's the t-test for dependent samples. Now, the t-test for independent samples has 2 or more, or excuse me, not more, 2 groups. 2 groups. So this had 2 times. This one has 2 groups. Okay, so in this case, we're comparing 2 independent, 2 separate groups. For example, people who take vitamin and people who don't take vitamin. For example, people from Moore, Oklahoma, and people from Enix, Oklahoma. I can't remember the other town right now. But people from 2 different towns in Oklahoma. Okay. All right. So now let's talk about the one-way ANOVA. How is the one-way ANOVA different? Well, it's the most similar to the t-test for independent samples, except now we have 3 or more independent groups. 3 or more independent groups. This is when we talked about our psychology majors, our physics majors, and our math majors, right? Independent groups. Now, the repeated measures ANOVA is most like our t-test for dependent samples. Now we have 3 or more times. 3 or more times, or 3 or more conditions that each person takes. So this could be at the beginning of the semester, the middle of the semester, the end of the semester. We take students and ask them their stress level. Or this could be putting people in a simulator with a phone, putting people in a simulator without a phone, putting the same people, remember it's the same people each time, same people in the simulator with an iPad. I think it was a handheld phone, hands-free phone, and no phone, but you get the idea. Same people doing different things, okay? All right, so that's the repeated measures ANOVA. All right, so remember, repeated measures, very similar to dependent. One-way ANOVA, very similar to independent. All right, factorial ANOVA. What's different here? Well, what's really different here is for the first time, we have more than one independent variable. This is the only test that we talk about in this class where we have more than one independent variable. So we not only look at whether vitamin to vegemin impacts energy levels, but whether gender does as well. 2 independent variables. This is when we can have an interaction where the difference can't be shown from just how one independent variable impacts the DV. You need to know both, right? They have a joint impact on the DV. So for example, if males given vitamin to vegemin lose energy, but females given vitamin to vegemin gain energy, that would be an interaction. Okay, because gender alone doesn't answer the question. Vitamin to vegemin alone doesn't answer the question. You need to know both. Okay. Let's move on to the next one. By the way, we do note at the bottom that the independent variable are qualitative and nominal, and the dependent variable is continuous. That's one more hint. Okay, all right. Now, the Pearson correlation coefficient and simple linear regression both involve 2 continuous variables. So that's your first step. Do I have 2 continuous variables? If you do, you've got one of these 2. So now, how are we going to tell these 2 apart? Okay, I've already identified the 2 continuous variables. How do I tell these 2 apart? Well, the easiest way to tell them apart is if it's a Pearson correlation coefficient, it's just going to talk about association or relationship. If it's a simple linear regression, we're going to talk about prediction. Predict, predicting, predicted, prediction. Okay, something around predict. Okay, that's really the big difference there. Okay. All right. But they both have 2 continuous variables, and they're both interested in those relationships and associations. It's just that simple linear regression takes it that additional step to talk about prediction. Okay. And then what we talked about today, Comparison of tests, 0 continuous variables, 0 continuous variables. So now we have our chi-square test for goodness of fit and our chi-square test for independence. What's different between these two? Again, once you identify, I have 0 continuous variables, and that should be your first step. Then you can go to this page. What's the difference? 1 qualitative variable, 2 qualitative variables. 1 nominal variable for goodness of fit, 2 nominal variables for a chi-square test of independence. Okay. All right. So those are your tests. Now, I just want to do a brief reminder about how you interpret statistical tests. Now, for the ones where we actually looked at a table, and that's only the z, the t, and the chi-square. We're looking for the score to be more extreme, more positive, or more negative. Now, that's true for z and t, but not true for chi-square. Why? Chi-square is always positive, so we don't have to worry about the negative. But for z and t, more positive or more negative than the table value. So you are trying to beat what's in the table. Your calculated score should be more extreme, further in the tail than what's in the table. If that's true, the result is statistically significant, and we are likely to reject the null. Why likely? Remember, we'll come back to it. If the calculated z, t, or chi-square score is not more extreme than the table value, the result is not statistically significant, and you are not going to reject the null. Okay. That's regardless of whether it's however it is. If you don't get to more extreme, definitely no rejecting, definitely not statistically significant. Okay. If the observed p-value or sig value, now this is for SPSS. The last one was for hand calculation. This is for SPSS. If the observed p-value or sig value is less than alpha, the result is statistically significant and you're likely to reject the null. Here's that likely again. Why do I keep saying likely? If the observed p-value is not less than alpha, the result is not statistically significant and you do not reject the null. So I'm going to, one more time, note this, it's not a contradiction, but it is a little bit counterintuitive. You're trying to be, when you're hand calculating, you're trying to be more extreme, more positive or negative than what's in the table. When you are doing SPSS, you're trying to be lower than alpha. You want that sig value to be lower than alpha, small, small, small. Okay. Okay, now, why did I say likely? Because it's an exception to the rule that if you have a one-tailed test and the results are in the opposite direction of what is stated in the alternative hypothesis, you do not reject the null. Let me say that one more time. If you have a one-tailed test and the results are in the opposite direction of what is stated in the alternative hypothesis, you do not reject the null. So if you said something was going to be higher and it came out lower, don't reject. If you said something was going to be lower and it came out higher, don't reject. Okay, and that's regardless of whether you have statistical significance or regardless of what is going on. Okay. So which tests again can we have one-tailed for? The Z, all the T's, correlation, simple linear regression. Which ones are only two-tailed? Nova, chi-square. Okay, all right. That is all I have for you guys for today. Stay safe, be well, and I'll talk to you again next time.